in the random sense, it's being generated by a lot of different sources, and there's nothing further we can do about it. In some sense, the Gaussian distribution has a kind of maximum uncertainty property about it. There's not a lot you can do with Gaussian noise other than just accept it as distortion. Now, the white part simply means that if I take the noise at any two time instants, call one t and the other s, and multiply it together, this is sometimes called the autocorrelation function for the noise random process itself. Usually this is a function of the difference between t and s. If it's stationary, that's certainly true, and we've said this is stationary. So the noise statistics don't change with time. That's kind of reasonable. If whatever those sources of noise are, if they're relatively constant with time, then we could expect it to be stationary. This is a delta function if it's white. And basically what that means is the power spectral density of the noise is flat. Looks like this. So if I were to write Sn of f, it looks like this. Two-sided power spectral density is n naught over 2 everywhere. That's why it's a two-sided power spectral density. If I did a one-sided power spectral density, it would be n naught is the parameter. And it turns out that this n naught over 2, we see the two used interchangeably, that works out to be the variance of the Gaussian noise. If you work through the probability distribution for the random variable, you'll see that this flat distribution, if we say it's white, is the variance of the noise itself. Now, the certain qualifications on that we'll get to later. Essentially, if you really look at this, the power of this noise, okay, is infinite. We got a power spectral density that's flat. But if we look over some normalized unit in time, or we look at any dimension, any basis function dimension, is going to be variance n naught over 2. So this is white noise. And this last thing about the noise. The Gaussian's okay, mean zero is okay. Those all have physical backup. Do we ever have noise that has infinite bandwidth? Well, no, not really. But when we say we have white noise, we're going to be saying that the noise is basically kind of flat, contributions at all frequencies, at least over the band of interest that our modulator works. And anything that's going on outside of that band of interest really is not so much of interest to us anyway in transmission. So we never get fully infinite bandwidth noise like this with infinite power, but nonetheless, it's a kind of an abstraction that will make the math easy, and we don't necessarily lose anything by doing this. Now, what we'll see at the end of Chapter 1 in Section 1.7 is a way to take noise that's Gaussian but not white. Sometimes it's called colored noise, white meaning all the spectrum is included. Colored means it has certain frequencies that are more heavily represented than other frequencies. So you can think of that as, if we thought of it in the visual spectrum as being colored. So you have these two terms. White means you have all frequencies. So anything that has all frequency looks white. Anything that has certain frequencies larger than other looks like it's some color. When we have colored noise, it turns out that reversibility theorem we just saw earlier, it's possible at the front end of our receiver to go through a filter that whitens the noise, and it will be a one-to-one filter. So it's reversible. And then we're suddenly back to the additive white Gaussian noise channel. So we can study additive white Gaussian noise. Even if it's colored, we're going to have a trick coming later that's going to get us back to the theory you see today for white noise. So this is pretty a general type of theory that will apply to any type of additive Gaussian noise, whether it's white or not, as we'll see. Now, the Gaussian distribution has a one more thing that I would like to mention on the power spectral density here that I forgot. This power spectral density, n naught over 2, is the PSD of the noise. And it turns out that for many systems where we simply have, say, a wireless transmission system or a wired transmission system where we look across some kind of load resistor in our receiver, and there's noise being generated in that receiving load of the system, That n naught over 2 is then produced by what's called thermal noise, which represents kind of a lower limit on the PSD. We may have other noises contributing, and you can always compute that as the Boltzmann constant, if you happen to remember what that is. I never do. I think it's like 1.38 times 10 to some power. Look it up in your physics book. But the and times T here is not the symbol period, but actually the temperature. So if we had, let's say, 273 degrees Kelvin, which is room temperature, and this is Boltzmann, then this turns out to be minus 174 dBm per hertz. And you will often see noise specified in terms of dBm per hertz as a power spectral density. Typical numbers for this in wired transmission, you see numbers minus 140 dBm per hertz, minus 150 dBm per hertz. That's 20 to 30 dB higher than this thermal limit. In wireless transmission systems, you'll see similar numbers, sometimes specified for this noise. It's very rare that you'll see it that low because there are other contributing factors to the noise other than just the thermal effect. If you can't go below this number, you can certainly reduce that number by cooling the front end of your receiver. You may have heard of very low noise receivers being cooled in liquid nitrogen or liquid hydrogen, liquid helium, and the lower the temperature you have, of course, the less noise in the system. But minus 174 dBm per hertz, if you see a number less than that, you'll know that doesn't make a whole lot of sense unless the receiver's inside a refrigerator somewhere. dBm is decibels per milliwatt. It's a term we're going to see used heavily in communications, and what it means when you see that term is you take 10 log the ratio of the power of the quantity referenced to 1 milliwatt of power. So dBm means dB referenced to a milliwatt. We'll see dB coming up quite a bit, and by the end of the course I'm sure you'll all be very familiar with computing decibel-like quantities. But we'll let that come as it may. If you see a level, however it's specified in units, less than this, that's too low in the transmission system. Now, the distribution itself, what will be of interest to us in transmission theory, is going to be the probability that the noise exceeds some value. The noise is big enough, it can cause errors to be made in a receiver. Okay, bigger noise, more chance that the noise takes me from the correct decision region to the incorrect decision region by making decisions. And so there's a function that actually characterizes this probability. It's called the Q function. It's in the appendix. We write down what it is. It's not something you can integrate yourself, so you have to tabulate it. And it's basically defined as the integral from x to infinity of a unit variance Gaussian distribution, e to the minus u squared over 2 du. Okay? And so it also corresponds to, obviously, the probability that the noise is greater than x times the variance, the square root of the variance, the standard deviation. And you can write this as q x over sigma, if you will. So essentially, the Q function allows us to compute probabilities that the noise has a certain size. Okay, it's tabulated in the appendix, or if you're using MATLAB, which most everyone does these days, this Q of x, you can actually get it directly in MATLAB by using what's called a complementary error function. They don't actually have the Q function in all the MATLAB packages, but they do have the complementary error function, and it turns out that this formula here, 1/2 ERFC x divided by square root of 2, will give you the same value as the Q function. But what it means is that a unit variant Gaussian exceeds it's the probability that a unit variance Gaussian random variable exceeds the value x that's in the argument of the function. So we'll be using that to quantify systems as we proceed. So this is the additive white Gaussian noise channel. That's its definition. We've got a few things that characterize it: the variance, the Q function, zero mean. Let's look at the demodulator and what it does with that noise. So we take discrete additive white Gaussian noise. It's going to be generated by taking a received signal y of t from the output of an additive white Gaussian noise channel and running it through the match filters that we saw earlier. Let's look at one of those match filters, phi 1, t minus t, and then we will sample that at time t equal to capital T. And since this is a linear filter, here this match filter, and clearly I could write that this is equal to x1 plus n1 at the output. Oh, I'm sorry. Yeah, unfortunately you got me on TV and we need the pad. There we go. Let me go back for a second there, sorry. I could see it. Unfortunately, you couldn't. We have the received signal y of t, and it has both signal plus noise in it. Since it's a linear system, we can look at the output of a single match filter as being the sum of the signal part. We already know what that is. You guys are going to know this demodulator produces x1, plus some noise. We'll call it n1. And we could, of course, do that for each and every one of the components that are used to specify the basis for the modulator. So I would be left with a vector of inputs being corrupted by a vector of noises producing the vector of outputs. Now, one of the things that we know immediately, if we have Gaussian noise on the input to a linear system, we still have Gaussian at the output. Okay, and if we sample that at some point in time, we'll find it's still Gaussian. It's Gaussian at all points in time. Then if we sample it, it's Gaussian at a particular point in time. So this N1 is still Gaussian at the output of the channel. Furthermore, if the input was zero mean, then going through a linear filter doesn't change that zero mean. We still have zero mean at the output. And in fact, if I were to look at the correlation between any two components of this noise, it's not too hard to show. You basically have to write down the two integrals for the two components, multiply those integrals together, which gives you a double integral, take the expected value, and then use the delta function or the autocorrelation function of the additive white Gaussian noise in continuous time, and move the expectation inside the integral. And what will happen is you will get this result. This is the discrete or Kronecker delta, that the variance in each of the dimensions is n naught over 2. So if you project white noise through any normalized filter, because remember, we had normalized basis functions. So they're still normalized here if I reverse the argument. I get n naught over 2 of variance in each dimension. And furthermore, since the original noise was white and the basis functions are orthogonal to one another, the component of additive white Gaussian noise on any basis function that's orthogonal to another basis function is independent of the component of that same additive white Gaussian noise on that other basis function. That kind of makes sense. Okay, things are orthogonal here. They're nice and white and even. We kind of get hit equally by white noise in all possible representations. Wouldn't even matter what the basis functions were. As long as they're orthonormal, then I get independent noise in each of the components. So this is basically also white, if you will, this vector channel that we've generated. Now the question is, with that, which is kind of easy to understand, okay, we got white noise, it projects uniformly in all orthogonal dimensions, and it's independent in all those dimensions. There is kind of a rest of the noise that we lost. We didn't lose anything about the signal in this demodulator, but we lost something about the noise. We projected it into capital N components. It's no longer continuous time. We get this nice white noise that's independent of itself at all points in time. We lost something here. This is something that's got energy in a lot more dimensions than just the basis functions that we were looking at. So what did we lose? Well, let's call that n tilde of t, and basically that's n of t minus whatever could be represented in terms of these components, n sub l times phi l of t. Of course, because we can certainly reverse that demodulator, and we have a modulator again, and this is reconstructing that part of the noise that we actually represented. Okay, because remember, there's any signal that can be represented in terms of these basis functions. We don't lose anything with these match filters. This noise has a component that is represented, but it also has another part which is not represented. Those basis. The difference is what we lost. Okay. Now, the kind of interesting thing is that if we take this approach, it becomes pretty easy to use the irrelevancy theorem. Okay, and there's a proof in the book of this. This is just a few lines here, and I find it's somewhat boring to go through it in class, but I think you're probably with me already. Is what I have to do is just call this y2. Yes, sir?
Sir, why did you consider it as components that are not represented in the basis?
Well, I'm considering them to show that they're irrelevant, basically. So I think you're jumping ahead of me. You're saying, why am I doing that? Because it's useless noise? Yeah, well, that's the theorem I'm about to prove. So if it's that easy, I don't need to spend too much time on it. But you've already caught the concept that I'm trying to get to. Because we could have maybe an infinite set of basis functions, as he just asked, and we would have components of the noise and all those other basis functions. Okay, and unfortunately, since those have nothing to do with the signal, that noise out there on those other basis functions, since it's unrelated to the noise on our basis functions, is useless to us. And it trivially is this kind of extra noise type thing that we saw in the irrelevancy theorem last lecture. Okay? Any noise that's completely uncorrelated with the noise that we had doesn't help. It was like that situation with the extra noise on the bottom that was uncorrelated. N2 was uncorrelated with N1. That doesn't bring us any information about the signal. If it were correlated, it'd be different. But it's not, and that was the third example we had on Thursday when it was correlated. But if it's uncorrelated, it's useless. And so all this other noise, basically, we could project it perhaps onto other basis functions that are orthogonal to the ones that we're using, but it's completely irrelevant. So if we were to set y2 equal to n tilde, and then apply the theorem that you, of course, recall here, and I'm going to write it down again, P of y2 given y1 x has to equal P of y2 y1 is one way of specifying this. Basically, all of these are equal to P n tilde. So it's a few lines to do that a little more formally, but you get the basic idea that since these two are equal, this part of the noise is irrelevant. And it's because this n tilde, you have to show that n tilde is uncorrelated with x. Clearly it is because it's noise, and that it's uncorrelated with y1, which is the noise n1. So if you take n tilde, take this function, multiply it by nl times phi l sub t, take the expected value. It's not too hard to show that that's 0. So it's uncorrelated, independent. The conditions of the irrelevancy theorem apply. What does this mean? This means that without any loss whatsoever in our design of an optimum detector, we can go through this type of match filter demodulator. Because any noise we missed, anything that was in the original noise that's not contained in the capital N discrete components of noise that we've created here, is irrelevant by the theorem. It contributes nothing to the map detector or the ML detector for that matter. Can't help us in making a better decision. So we've lost nothing on the additive white Gaussian noise channel by going through the demodulator like this. So that justifies our looking last Thursday at the vector channel itself as an equivalent to the original channel. We can in fact get it back to essentially a discrete representation that's easier to deal with than all those continuous signals. And that's in fact what we did. And we proceeded to design detection rules, okay, that basically maximize a probability function that were based on this vector channel as opposed to the original continuous channel. Let's look at some examples of this. Just to kind of build our intuition that we're okay here. We got X, we get some noise in one vector channel, got an output Y1. Clearly the conditions of the irrelevancy theorem apply if we have N2 going to Y2 and this noise is completely independent of that noise, and this one doesn't help us, throw it away. Let's look at that maybe more realistically in terms of a transmission system. Suppose we were to take Fourier transforms of all of the modulated signals, and we were to look at them in the frequency domain. What do they look like? Well, we might get signals that